Hariom children, in the last videos, we just started with wave optics. I gave you the Huygens wave theory, Huygens principle. Using Huygens principle, we proved the laws of reflection and refraction. Now next is we are going to go into another important concept. Before that, you have a small assignment. Under the laws of refraction, while we were proving Snell's law, we saw that light travels from rarer to denser. Now you have to draw a figure where light travels from denser to rarer, and you have to prove the Snell's law. This is an assignment for you. Now the next important thing I wanted to say is whether it is reflection or whether it is refraction, the frequency of light always remains the same. So why do you say that the frequency remains the same? It is because the time remains the same, and since frequency, which is a function of time, also remains the same. Let us prove that in both these cases. Now, under the laws of reflection, what is a wavefront? It is the envelope of all the points which are in the same state of vibration. So here, ABC is an incident wavefront. The time taken for each and every point of the incident wavefront to reach the reflected wavefront is the same. That's why we said that CD is equal to AE. The time taken for each and every point of the incident wavefront to reach the reflected wavefront is the same. The time taken for A to E is the same as the time taken for C to D. The time taken for G to F is the same as the time taken for B to G. So for each and every point in the incident wavefront, there is a corresponding point in the reflected wavefront which arrives in phase, and the envelope of all these points gives the position of the new wavefront. So since the time remains the same, we say that the frequency, which is a function of time, also remains the same. So this is the same as in the case of reflection. If a ray of light is incident, then immediately it gets reflected. The time taken for incidence is the same as the time taken for reflection. Therefore, frequency, which is a function of time, remains the same. Similarly, in the case of refraction, the time taken for each and every point of the incident wavefront to reach the refracted wavefront is the same. The time taken for C to D is the same as the time taken for A to E. See, the distance covered is different because this is a rarer medium and this is a denser medium. But the time will be the same. Therefore, the time taken for C to D is the same as the time taken for A to E. The time taken for G to F is the same as the time taken for the point from B to reach G, which means that the locus of all the points which arrive will be in phase. That gives the position of the refracted wavefront. So since the time remains the same, frequency, which is a function of time, also remains the same. We also know that the wavelength or the velocity of the light depends upon the wavelength. So we know that V is proportional to lambda. So to remove this proportionality sign, we introduce a constant. That constant is nothing but frequency, which means that frequency is always the same whether it is reflection or refraction. Now let us see what will happen if a plane wavefront is incident on a prism. Now let us consider a prism. So a plane wavefront is incident on a prism. Let us see what will happen if a plane wavefront is incident on a prism. We have to find out what is the shape of the refracted wavefront. The phenomena taking place here is refraction. So we have to find what will be the shape of the refracted wavefront. Now you know that whenever you draw a wavefront, the rays are always normal to the wavefront. So this is one ray. Let me consider 3 rays over here. And I'll mark this as, and let this be the position of a plane wavefront. I'll name this as DEB. So DEB represents a section of a plane wavefront that is incident on this prism. So, we have to find out what is the shape of the refracted wavefront. Now, we consider 3 points D, E and D of the wavefront. The point D of the wavefront, it has to travel a larger distance, and at this edge it just undergoes refraction. Therefore, even after refraction, it will travel the same distance. If you consider the point E, it travels partially through air. Then it will take a longer time to travel through the prism. So after coming out of the prism, it cannot travel a longer distance. It can travel a certain distance only after coming out of the prism. If you consider the point B, it travels entirely through the glass itself. So in order to compensate for the time, it has no time to come through the air. So what will be the shape of the wavefront? The wavefront has to be a plane wavefront once again. See, if you consider the point D, the time taken for D to D dash to reach D dash is the same as the time taken for E to reach E dash is the same as the time taken for B to reach C. Since it is traveling completely through the medium, there is no time for it to travel after a longer distance in air. So from here we start, because the time taken for B to C must be the same as the time taken for E to reach E dash and the same as the time taken for D to reach D dash. The envelope of all these points will be a plane wavefront. So when a plane wavefront is incident on a prism, we get the refracted wavefront to be plane once again. Now you have one more thing. Suppose if you have a convex lens and a plane wavefront is incident on a convex lens. So this is the ray and this must be the wavefront. I'll mark it as A, B, C. Now you have to guess what will be the shape of the refracted wave.